There are n children sitting in a circle, and during this game, repeatedly k children are skipped and one child is removed from the circle. So we skip the k children and then the child is removed. In which order will children be removed? We need to display. Let's see with let's take n is 7 and k as 5 as example. So we'll skip 5 children. So we'll start from here. We'll skip 5. So 1, 2, 3, 4 and 5. So we skip 5 and we display 6, and we will remove this. Again skip 5. So 1, 2, 3, 4 and 5. So we'll display this 5 and we'll remove this. Again skip 5. So 1, 2, 3, 4 and 5, and we'll display 7. Again skip 5. So we'll remove also 7, and then 1, 2, 3, 4 and 5. So we'll display 2 and erase. We'll display 2 and erase. Again 5. So 1, 2, 3, 4, 5. So we'll display 1 and we'll erase it 1. So again now we are left with 2 children, 3 and 4. So we'll remove, see, 1, 2, 3, 4, 5. So we'll display 4 and we'll remove, and since 3 is only left, we will display this. So I think the picture is very clear. We have children from 1 to n. We skip k. We display, then erase, display and then erase, and this we are doing in a loop, continuous. We are rotating. Let's see now how we can proceed. Okay, so let's study this example deeply. I have written this in linear fashion and these are the index. So you will start from this. These are index base 0. So you have to skip 5 children. So 1, 2, 3, 4, 5. So if I say index as 0, since we are starting from here, so index is 0. So you have to skip index plus k. It's correct. So if you do 0 plus 5, 0 plus 5 will make you reach here, and you have to remove this 6. So you skip display and then you are removing, so erase. We need to follow these 3 steps only to do so. So I have skipped index plus k, then I have displayed, and then I have erased. Now your index is this. You are standing at this position. Now you need to go. Now you have to do the circular rotation in this array. How you can do that? We use modulus operator to do so. So if I do mod of this with let's call this array as children. So children dot size. If I do mod of this, then I can rotate circularly on this array. Let's see how. So n is 7. So children dot size is 7 in the initial pass. So index is 0. 0 plus k. 0 plus 5 is 5. So this will go 0 times. So your index is at 5. So you skipped, you displayed, and you erase. Now this is not your when you remove this, your new array will consist of 1, 2, 3, 4, 5 and 7. 6 is gone. So this is your new index, 1, 2, 3, 4 and 5. Now you need to skip 1, 2, 3, 4, 5, and you need to display 5. How you gonna skip? So your index is at 5. So index is 5 currently, right? So index is 5. So 5 plus 5, k is 5, will give you 10. And what is the children dot size? This is our new children array because we have removed 6. So this would consist of 6, right? 6 elements are present. So 6, so 10 mod 6. So 6, this will give you 4. So your index position will now be 4. You will be present here, and you can clearly see also 1 1 2 3 4 5. You have skipped 5, and now you have to remove this 5. So you skipped, you will display 5, and then you will erase. So this 5 will gone, and this is how we will keep on rotating over this children array. So the conclusion comes that you need to do the skipping, which we are doing from modulus operator, simple, and then we need to display, and then we need to erase. So we need to perform these 3 operations, and these 3 operations are very simple. We can use any data structure, but we are not gonna use any data structure, and this is the key thing which this problem wants to make us understand, that if you look over the constraint, I think it is around 2 into 10 to the power 5. So skipping is okay, displaying is okay, and then when it comes to erasing part, then the time complexity of the traditional data structure which we use, let's say vector set, is O of n. And so you will have one loop for iterating over the children array, and other one which will be inside is for erase. So this takes n, because you need to take care of the complete children array. So this will go up n, and this erase has inbuilt time complexity of n. So totally they will make the things n square, and clearly you won't be doing n square here, because that will lead to 10 to the power 10, and in 1 second you can do up to at most 10 to the power 8 operations. Therefore we need to come up with some better algorithm or some better data structure. So we will use here some better data structure, and that is policy based data structure which we are going to use, and that will make the erase operation to go in log n time complexity. So I think and this is going to up to n, so total time complexity would be n log n, and I think we can go for n log n, because if you do because 10 to the power 5 log 2 into 10 to the power 5. So even if you take it as equivalent to 10 to the power 6 or 7, then this is less than 10 to the power 8. So we can go for n log n. So we need to come up with some data structure which can make our erase and displaying in the complexity of log n. So we have this policy based data structure. What is this policy based data structure, and why we are using it? So first key point is this, that this G++ compiler supports some additional data structure that are not the part of the standard C++ libraries, and these are called policy based data structure because you define some policy on these data structure. So we can remove and add elements, can find the number of elements less than x. These are some frequent used operation or use cases of these policy based data structure. We can find the kth smallest element. We can index it like an array. So if you are using set or any other these type of data structure, you can index it like an array, and all this happens in log n time complexity, and this is huge. From o from o on complexity, we are bringing it to o log n complexity, and this is huge. And we clearly saw in the previous slides that if this happens, then we can definitely do our solution in better time complexity. So this policy data structure is simple. We are using this just to overcome the problem of time limit exceeding. So let's look how we are going to implement over here. So policy based data structure, ordered set is one type of policy based data structure. You can define it for multi maps, but we are defining here for ordered set. And let's see. So we know set is a data structure that keeps the unique elements in sorted order. So this ordered set is going to perform all the operations which are being performed by traditional sets, but those additional operations such as erasing, which set takes o log n, not o n complexity, the set takes this ordered set, which we will define using policy based data structure, will take log n. So this log n time complexity helps to make things more faster. So this order set will have all the properties which set has, but but they raise in log n time complexity, and it support two additional function, which is order by key and find by order. So what is order by key? It gives number of items strictly smaller than x. So let's take some example. Let's say 1 2 5 7 is there. Then if you say order of key on 6, then you will have 1 to 5 as your output, not 1 to 5 but the number of items, which is 3. This will be your output. And also it has the second function, which is find by order. This gives the x element in a set. So this is what we need, right? We have the index, so we can use find by order over that index, and it will give the x element occurring in the set and counting from 0. So now we can see that set are like indexed arrays, first thing, and second thing, this is occurring in log n time complexity. So how we are going to use this order set? First of all, we need to include two additional header files, which is associate container and tree policy. So this associate containers is like a group which has set multi maps, these type of data, associative data containers. So we include this because we are going to use this set as associative container. And then we have the tree policy. What this tree policy is? So this tree policy has this definition, this template which we need to use. So don't be scared of this. This is just writing how we used to write, like vector, and then here vector, and then here we define the object and then the name. Similarly, let's see. So here if we do the comparison here, so we are writing here tree, then we are defining this, and then we are giving a name to it. So this first thing tells this that what type of keys you are going to use. It can be float, it can be a pair of integer. So here we are using simply integer. Then this second parameter has null type, so it tells the mapped policy. If you are using for set, if you are using the set, null type will go. For other policies such as mapped policies, for using map you will use mapped policy. So this is just null type. Then this gives the comparison. So here we are using less. This is basically comparison between two functions, so we will use less. And then this is the tells the tree. So basically this is what giving us log and time. We are using red black tree tag here. So this defines the tag of the tree we are using. And then this is like it has the metadata to manipulate the tree nodes, tree policy. This tree order statistic node update. And so this is how this template is. And what is this type def? So if type def basically replaces all this with ordered set, right? Like if I write type def of int as, let's say, what, I. So this int is giving the, now I is has the alias of int. In the similar fashion, this whole bunch is an alias. This ordered set is an alias of this. So this is how we will write. So now it's time to write the code. There things would be more cleared. And to summarize, it's simple. We are just skipping using modular arithmetic, then we are displaying, and then we are erasing. But we can't go and use the traditional data structure which we have, because the time complexity is more. So that's why this PBDS policy based data structure we are using to overcome the time limit exceed error. And if you are overwhelmed to see all these things, then you don't have to worry, because this all you can just memorize, or while practicing you will remember this. If not, you can just write, and for the time being just try to practice this. Okay, so this is associated container for for defining the containers type of using, then this tree policy which is used for manipulating the nodes, and this is the template. So now we will have a practical implementation of this. So we have the input as n and k, and n integers, the removal order we have to display. Okay, so so this is and this is what we used to have. Then these are additional uh, in additional we need to do for using the policy based data structure. And this is our uh, definition of the structure, data structure, and this is the name. You can put any name over here. I'm going for ordered set. So let's have the n and k as 0, then n k, then let's define our order, this order set, and call it children. So for this, so this is our policy based data structure, and this is the name of the data structure. Now we need to fill this with numbers from 1 to n. So let's do that. We can go with for simple I is 0, I is 1, I is less than equal to n, and I plus plus. And then we can do children dot insert I. So this will fill our data structure from 1 to n. Then let's create a function Josephus, and we will pass children the key and the index. Since in the beginning index is 0, so I can say index is 0. Now we will write this Josephus. Over here we can write, it has to return nothing, so I can simply, and now this has to accept children. So what we can do is we can pass this by reference ordered set. So this way we don't have to make a copy. This is passed by reference. That means this is going to point to the same children. We are saving the memory this way. Then we have to accept k and the index. Okay, so we need to calculate index, right? So index can be calculated by simple index plus key, and then doing a modulus operation children dot size. So this will make sure the skipping is going correctly. Then we need to display, right? We need to display the element present at index, at this index. How we can do that? We have this find by order, and it does, it basically it gives the x element in a set counting from 0. So I have the index, so if I do find by order at that index, I will get that number. So I can simply do children dot find by order, and I can give the index. And this we need to do star to access the value present there. So we do this and then give escape. Now we need to erase. So we have a inbuilt function children dot erase. This is the same, and then what we have to erase, we have to erase this element. So we'll copy this and we'll just simply dump it over here. So this will make sure that the children of this number is erased. After doing this, again we can call this, since this is a repetitive thing we need to do, so we can call this function again. So we can call this function again, but when this condition when this has to stop, it has to stop when the size is becoming 1. So if children dot size is equal 1, then we need to display, since this only one element is present, one element is present, we will do C out of this, and since one element is present, the index would be 0. Simple. right? Because this policy based data structure allows indexing also, so we can access this by simple, like we used to do in the vectors arrays. So you see how simple it became when using this data policy based data structure, and we can return. So this was the simple explanation. We are using this policy based data structure we defined over here, and this is the model, and this is the alias. Then we filled, and then we are doing the skipping. Find that element, erase that element, and then again call that until you are left with one children. As soon as you are hitting the one children, you just simply display, because you have already you kept on erasing the children, so you must be left with only single children at some point of time. Then you display that and just return. So now let's try to submit this. Submit. So this is present at Josephus Problem 2. Not here. Send this Josephus Problem 2. .cp. And you must be wondering, can we do the this? Okay, let's just. Can we do the same thing in the Josephus Problem 1? I have made a video by using a different method, different way, but we can use by this method also. So this has been accepted. So let's try to do Josephus Problem 1, which I have made a video earlier using the different method, but we can apply this method also, because this is just the Josephus Problem 2 is the extrapolation of problem number 1. Here we were every alternate child is being removed. So it is written somewhere, every second child is removed. Every second child is removed. So alternate children means you have to leave one, right? So I can do some manipulation here. So instead of accepting here, I can say k is 1. So since alternate children you have to leave only one children. That's why I am using k as 1. Other than that, I don't think so. We don't have to make any changes because the code remains the same. So let's try to submit this. So Josephus problem, no, not this one. The name is same only. Josephus problem number 2. Okay, submit. So it has been accepted.